now see how we can use finite difference technique to convert the differential equations, in this case the boundary value problems, to what we call difference equation. Difference equations are nothing there, simply set of linear equations, Ax equals b type system, which will come from our original ODE d2 theta dz2 minus m square theta equals 0. And if we look at this Ax equal to b system, we'll see that we will have lots of equation. In every equation we will have three unknowns like this, and this is the sort of equation which are coming out of discretization of the ordinary differential equations. These are called difference equations. Let us recall our discussion in last lecture. We are talking about governing equation d2 theta dz2 minus m square theta equals 0, and we will have two compatible boundary condition. One is theta at z equals 1 equals 0, and another is theta at z equals 0 equals 1. The physical domain goes from z equals 0 to z equals 1, and when we discretize the domain, we take this discrete grid points. Under the assumption of uniform grid size, we will have this zi plus 1 minus zi is delta z for all i's. So if I have here I, this is I plus 1, this is I minus 1, the difference between two consecutive grid points will always be the same as delta z. So under such situation, we would like to discretize the differential equation. So let's see how we can do that. We see from this equation here, I come here. Here you see that d2 theta dz2. From our discussion of numerical differentiation, you know that we can discretize this using central difference as theta I minus 1 minus 2 times theta I plus theta I plus 1 divided by delta z square. Then I have m square theta. This m square theta will simply take at this theta I. So this is a discretization at ith point, and this is equal to 0 on right hand side. Since this is a discretization at ith point, we can go from I equal to 2 to I equal to n minus 1 with this. So I have this here, I have I equals 1, and my last point is I equals n. So for the inside points 2 to n minus 1, I have this discretization. Now what happens to I equals 1 and I equals n? For I equals 1 and I equals n, we will apply boundary condition. We are coming to that, but first let us look at this equation here. This equation contains theta I minus 1, theta I plus 1. All three are unknown, and we can simply write this in the form of theta I minus 1 plus b theta I plus theta I plus 1 equals 0, and this b, you can check it here that this is, there is minus 2 and minus m square delta z square. So if I multiply both sides by delta g square, then right hand side is 0 anyway. So right hand side will remain 0, but left hand side this m square theta I will be multiplied by delta g square. So my b is minus 2 minus m square theta j square, and I have this equation theta I minus 1 plus b theta I plus theta I plus 1 equals 0. Now we come to the boundary condition, which will be I equals 1 and I equals n, and these are very simple because here I know that theta equals 1 at z equals 0, and z equals 0 corresponds to I equals 1. So for I equals 1, theta I equals 1. Similarly, theta I equals 0 for I equals n. So now we have a complete set of differential equations. We have n equations with n unknowns. My equation 1 is this, theta I equals 1 equation n is this, theta I equals 0. And then from 2 to n minus 1, I have this theta I minus 1 plus b theta I plus theta I plus 1. So to overall I have n equations, and theta I are my unknown, and I goes from 1 to n. So I have n equations, n unknown. In principle, I can solve this equation using some of the techniques that we have learned before. These equations are also called difference equations since they are obtained from finite differences. Okay then, so let us now see what we will do about it. So I have a set of equation for I equals 1, theta I equals 1, I equals 2, theta I minus 1 plus b theta I plus theta I plus 1 equals 0. For I equals 3, theta I minus 1 plus b theta I plus theta I plus 1 equals 0, etc., etc., up to I n minus 1, theta I minus 1 plus b theta I plus theta I plus 1 equals 0. And finally I equals n, theta I equals 0. So this is an Ax equals b system. How does it look like in matrix form? Now look at this matrix. Here in this matrix form, I have the diagonal will be theta I. So the diagonal is populated. In the first equation, the diagonal is the coefficient of theta I is 1. So I have 1 here. Then from 2 to n minus 1, coefficient of theta I is b. So I have all these b's here. It goes up to n minus 1. So this is my I equals 1, then this is my I equals 2, etc., etc. I equals n minus 1. So all the diagonal terms becomes b. Then the last equation theta equals 0. So I have 1 here. Now you see that in first equation, the theta equals 1 is the only thing that we have. So I have 0 here and nothing else. In the second equation, I have b theta I, and then the term just before theta I is theta I minus 1. It has a coefficient of 1. So coefficient of 1 appear here. Then the next term, theta I plus 1, it also has a coefficient of 1. So coefficient 1 appears here. So you can see that all subsequent rows, I have this 1b1, 1b1, 1b1 up to n minus 1. Then for I equals n, I have only theta I equals 0. So nothing really here. Now you can look into the structure of the matrix. You see that I have these 3 diagonals, then left side of diagonals, right side of diagonals, everything I have is here. Other than that, the matrix is full of zeros. On the right hand side, I have the first term is 1, then all subsequent terms are zeros. This is the type of matrix. Here I have this n grid points, we have n equations, n unknowns, and n by n coefficient matrix. Total number of elements will be n square. However, the number of non-zero elements could be, at best you can think of about 3 times n or so. It would be actually less than 3 times n. It can't be greater than 3 times n. So overall you can think of that if my n is, for instance, 100, then the number of elements in my coefficient matrix for n equals 100, it would be n square will be 10 raised to 4. But number of non-zero elements will be of the order of 300. So within this n square 10,000 elements, only 300s are non-zeros. So most of the elements are zeros. So these are the type of matrix we call sparse matrix. That means they mostly contain zeros, only few non-zero elements. And in most cases, when we will solve ODs or PDs, we will encounter sparse matrices. This is very important. The matrix is not populated, and we have to look at certain algorithm which will be efficient for sparse matrices, or in other words, it means that which will maintain the zeros. We don't want to change the zeros to non-zeros while solving this system. That will be an inefficient way of solving. The other point about this coefficient matrix is that this coefficient matrix is what we call is a tridiagonal. So tridiagonal matrix is that all the non-zero terms will be populated at the diagonal and just right side and just left side of the diagonal. So these are the type of matrix it's called tridiagonal. And in this sort of equation, you see that with one independent variable, so ordinary differential equation, as well as if we have in some special cases in partial differential equation, you will see later on that will generate tridiagonal matrix. So we have to look for certain algorithm that will solve the tridiagonal matrix efficiently. Another important factor here is that because the matrix is full of zero, we never store this n square full matrix. Instead, only the non-zero terms will store. So the storage as well as the solution methodology will be based on this sparse tridiagonal system. We will not go for a general Ax equal to b solver. We will see that some solvers that will be more or less tuned towards sparse tridiagonal type matrices. For your exercise, I wish you to go to our initial discussion of linear algebra and look at the Gaussian elimination. Go online and review the storage possibilities of sparse matrices, how sparse matrices are stored. And then you must have your old Gaussian elimination program. Use that Gaussian elimination program and now you solve this linear equations here. Although they are sparse matrix, but we use the standard Gaussian elimination and solve them. And let's see how it works. That's all for this lecture. Thank you, and I'll see you in next class.